Today we are going to put all the information that we have learned in Chapter 3 all together to graph a function, or to graph multiple functions in this particular video. Now you can think of this as just a way of graphing things by hand, or you can think of it as a way to basically just pull all the information about a function out of it. Either way, let's review what we have so far to work with. And I'm going to break this up into 3 different categories. First thing, we're going to talk about the function itself. From the function itself, we could look at the domain of the function, and potentially even the range. Though the range is usually a lot harder to get than the domain is. Domain is usually a lot easier of a question. So most of the time we'll just leave range up to how things work out, and maybe don't worry too much about that specifically. We can also ask what are the x and y coordinates, or not coordinates, x and y intercepts, sorry. Basically, where does this function hit the x-axis? Where does it hit the y-axis? The y-intercept is usually pretty easy to get. You just get to plug in 0 for the x and see what y you get. X can be a little bit more complicated. You'll have to set the function equal to 0 and solve for your x-intercepts. Because we are looking for x-intercepts, we can also actually ask the question, where is the function positive or negative? Now, you probably haven't just sat down and done that for a function before, but it's actually going to be very similar to things that we have been doing throughout this chapter. So I'll show you how that goes as we proceed with all this stuff. Finally, the reason we brought up the last section, we might also have vertical or horizontal asymptotes. Of course, if our function is a polynomial, we won't have those, but if a function that we are working with has asymptotes, we probably want to be able to talk about them. Now, all those are things that we can actually get directly from the function without actually having to do any differentiation. Now, technically, with the asymptotes, we are dealing with limits there, and so we are using some form of calculus at least. But now let's move on to the actual derivative. From the derivative, we can look at critical points. And looking at critical points basically means that we're looking at relative extrema. A relative max or relative min, all that kind of interesting things about a function. And in the course of actually looking at these critical points, we're also looking at where this function is increasing or decreasing. Because here we're essentially asking where is the derivative positive or negative. Sort of like what we were looking at the function being positive or negative. Here we're just kind of elevating that to the derivative instead. Finally, we can look at the second derivative. With the second derivative, we can essentially do the same things that we did with the derivative, setting it equal to 0 and looking at where it doesn't exist, in order to identify what we call inflection points. And then comparing the second derivative to 0, or comparing it to seeing where it's positive or negative, we can see what is the concavity of our original function. So you can kind of note here that we are repeating some of the processes each time. When we're actually looking at where the function is either where it doesn't exist, or it hits 0, we're looking at, well, for 1, we're looking at what its domain is, and we're looking for the x-intercepts. And then we can use those ideas to see where it's positive or negative. When we do the same thing for the derivative instead, now we're finding critical points of the original function and asking where the original function is increasing or decreasing, And then finally, with the second derivative, again, the exact same process identifies those inflection points in the concavity. So a lot of repeated ideas going on in here, but they have different meanings depending on which one of these three functions that we're looking at, whether it's the original function or its first or second derivative. What we're going to do for these problems is investigate all this information about our functions. Note that in actual practice, it's not always required to go through all of this. Sometimes it's actually a little hard to get some pieces of information, such as maybe for one of these when we set it equal to 0, it's hard to solve for x. Maybe in those cases we wouldn't actually try to finish solving that, but try to see what information we can get from the other parts. So we get as much information that we can in order to graph the function as well as we can. But once again, this will all be a lot easier to see what's going on when we actually put it into practice. So let's move on to an example. Let's look at problem 4. Here our curve has the equation of y equals negative x cubed plus 3x minus 2. Now, first we can note that since our function is a polynomial, its domain is all real numbers. Always want to start with the domain. Always start with what numbers make any sense to be put into this function. Well, I'm actually going to leave some blank space here. This will be the page that we're going to put all of our information about the function on, so we have a nice summary of all the stuff and can graph it right away. On another page, let's go ahead and look at where this function actually equals 0. Basically, where is negative x cubed plus 3x minus 2 equal to 0? Now, this is a cubic, and there is a formula for solving cubics similar to the quadratic formula, but it is a little bit more involved, and most people don't just know it off the top of their head. I actually would have to go and look it up if I wanted to actually do that. In this particular case, we don't really need it because we can make a guess, and an easy enough guess, and see what actually happens. For instance, if I were to plug in x equals 1, I'd have negative 1 plus 3 minus 2. That does give me 0. So we actually get to guess x equals 0 as a solution. Now, there are some techniques from algebra that can actually tell you what guesses are even worth trying. I'm not going to get too much into that here. But once I do actually have one solution to a polynomial, I can actually use that to decrease my degree. Essentially, I'm going to divide out by x minus 1, because I know x equals 1 means that it has a factor of x minus 1. I'm going to do that using synthetic division. If you don't remember how this works, just kind of either look it up or just kind of follow along. I'm going to put the x equals 1 here. I'm going to take my coefficients. Remember that there is a missing square term here, so I'm putting a 0 for that. Then I take the number here, I bring it down here. I take this number and I multiply it by the number here, which doesn't really change it. I put that here and I add it to the number above it. 0 plus negative 1 gives me a negative 1. The negative 1 times 1 again gives me another negative 1. Negative 3 plus negative 1. Why did I put a negative 3? There should have been a positive 3. Sorry about that. So 3 minus 1 gives me a 2. And then this 2 I'm going to multiply by 1. Should have been negative. I completely swapped my signs here, apparently. I'm going to take that 2 times the 1 here. I'm going to get a 2. And when I add those together, I get a 0. In fact, the fact that I got a 0 here is really just saying that x minus 1 is actually a factor of my original polynomial. And what this part here says is that when I actually do factor it out, going to have a factor of x minus 1, and the other factor is going to be negative 1 times x squared minus 1 times x and plus 2. So we're able to pull out that factor. I'm going to go ahead and pull a negative out just because I don't like having the negative in front here. I'm going to have a negative times an x minus 1, and then this x squared plus x minus 2, you can actually factor that as well. It has the factors of x minus 1 and x plus 2. So that part's just a quadratic. Hopefully you remember how to do that. But since we're setting this equal to 0, we want this original polynomial to equal 0. We're actually asking what are the actual x values that make the 0? Well, that's going to boil down to 1 from either one of these two factors and negative 2. I'm going to go ahead and put these into a number line. I'm going to put this over here. So I'm going to have a number line. I'm going to put on my numbers of negative 2 and 1. This is a number line specifically for the original function. I'm just going to put a y here to label that. We're going to have similar number lines for both the first and second derivatives. So I want to label my number lines so I know which one corresponds to what. But I also need to take test points. So in my intervals of from negative infinity to negative 2, and from negative 2 to 1, and 1 to infinity, I'm going to pick numbers in each of these because my function has to always be positive or always be negative on the interval from negative infinity to negative 2. That's what I know from the fact that these are the only places it hits the x-axis. And my function is continuous. There's no discontinuities in a polynomial. So let's just go ahead and plug in negative 3. Remember, our function here was this here, negative x cubed plus 3x minus 2. If I plug negative 3 into that, negative 3 cubed, that actually turns into a positive 27. 3 times negative 3 is going to give me a minus 9. And finally I have a minus 2. That gives me a total of 16. I don't care that it's 16, but I do care that it's positive. So I'll put a plus sign here. From negative 2 to 1, well here, because I also want to know what the y-intercept is, this is a perfect opportunity for me to go ahead and just plug 0 into the function. That will actually give me my y-intercept. If I plug 0 into my function here, these first two terms go away, and I'm left with a negative 2. So specifically, not only do I know that the function is negative from negative 2 to 1, but we also have a y-intercept of negative 2. Finally, from 1 to infinity, let's go ahead and just pick 2 as our test point. Plugging that into here, I get a negative 8 plus 3 times 2 is 6 minus 2 gives me a negative 4. So my function is also negative here. It didn't actually alternate at 1. Alright, let's move on to the first derivative. Now, of course, we have our original function. We had y equal to negative x cubed plus 3x minus 2. I can go ahead and differentiate that pretty easily. The derivative of negative x cubed is negative 3x squared. Derivative of 3x is just a plus 3. And the negative 2 goes away. I want to set this equal to 0 and solve. This one's actually a lot easier to solve than the last one. Basically, we have 3x squared has to equal 3, because of that negative there. Which means that x squared is 1, or x is plus or minus 1. We can go ahead and put a number line for that first derivative. We know that we have plus or minus 1. Now, some people like to try to line up the number lines so they actually correspond to each other. I'm not going to bother doing that here. It's only moderately helpful. But I'm going to take test points for these intervals. from negative infinity to negative 1, from negative 1 to 1, and from 1 to infinity. And plug those test points into my derivative. Well, I can just go ahead and pick negative 2, 0, and 2 for our test points. If I plug those into my derivative formula, negative 2 squared is a 4. Negative 3 times 4 gives me a negative 12. But I need to add 3 to that to get a negative 9. In fact, we're going to get the same result for 2 because the square got rid of the negative anyways. We get negative 12 plus 3 to get a negative 9. When I plug in 0, on the other hand, this term goes away and we're left with the 3. So we have negative for the terms that go off to infinity, or the intervals that go off to infinity, but we have a positive for the middle term. And actually at this point, from our number line, we can already determine some stuff about the particular curve. We know that it has to have a relative minimum at negative 1 because it was decreasing and then increasing. And at 1, it has a relative maximum because it's increasing and then decreasing. That's all thanks to the first derivative test. Then we also can look at the second derivative. Just differentiate negative 3x squared plus 3 again. The 3 goes away, and this becomes a negative 6x. This is even easier to actually solve when we set it equals 0. We just have x equals 0. And we're going to have intervals from negative infinity to 0 and from 0 to infinity. I'm just going to go ahead and take test points right away. Just going to go ahead and pick negative 1 and 1. Just 2 points on the either side of 0. If I plug these into my second derivative, negative 1 times negative 6 is a positive 6, and 1 times a negative 6 is a negative 6. So this time, I have a second derivative with only 1 point on my number line, and it's positive over here, and it's negative over here. We do actually have an inflection point because the concavity actually did change at 0. So, now we get to put all this information. We have a lot of information about this function already just shown on this page so far, and we're going to take all of it and graph our function. The first thing I want to do is plot all the significant points. These are the intercepts, the critical points, and the inflection points. So first things first, we have our y-intercept. We have a y-intercept of negative 2. I'm going to put that here, negative 2. I'm going to put that here. This is our y-intercept of 0, negative 2. We also have x-intercepts. Those are at negative 2 and 1. So let's say here at 1, and here at negative 2. I'm kind of hesitant to put the labels here just because I don't know exactly where my graph is going to, whether it will pass through one of them. But let's just go ahead and do that. We have 0, 1. We have negative 2, or we have 1, 0. We have negative 2, 0, and we also have 0, negative 2. Those are points on our graph. They're all the intercepts of our curve. Our curve can't hit the x-axis anywhere else. Definitely can't hit the y-axis anywhere else, or it wouldn't even be a function. I know that it has to be positive from negative infinity to negative 2, so it's up here somewhere. Don't know exactly quite yet where, but you might be able to guess already a little bit. I mean, we've already got a lot of information just from that. We know that it goes negative. It definitely goes negative. And then it actually stays negative after from 1, 0 onward. So actually putting the 1, 0 up here actually was fine. It definitely is not going to go above the x-axis. You'll actually just touch there. I know that it has to be decreasing from negative infinity to negative 1. Well, negative 1, well, it's going to be somewhere in here. But what is the y value at negative 1? What is that relative minimum that we talked about before? Well, if I plug -1 into here, I'm going to get an answer. It's actually going to turn out to be, say around here, the y value there is -4. So it decreases, it passes through this point, and it hits down here at -4. Or at x equals at -1 with a y value of -4. Then it has to start increasing until it gets to 1. We don't actually have to write out what that, we don't have to figure out what that point is. It was already an actual intercept, so we already graphed that point. Finally, we also want to talk about where the inflection point is. That's when x equals 0. But we already have that one here as well. At 0, we have an inflection point at 0, -2. Our function has to be concave up, which means it has a cup shape to it, all the way from -infinity till we get to 0. So actually, we already kind of have a good idea of what the shape looks like. It has to go through that point, it has to bottom out here, and it has to have this cup shape to it. But at 0, it now has to have a cap shape. Now it has to start curving downwards. And it has to max out at 1. So we're going to have something that kind of looks like that. And it has to decrease from that point on. So how good of a graph did we actually get? Well, we could go ahead and actually graph this using the computer just to test our answer. So recall our function was y equals -x cubed plus 3x minus 2. And we had our significant points on this were 1, 0, -2, 0. Those were our x-intercepts, and one of them was actually a relative maximum. We had a y-intercept of 0, -2, and we had a relative minimum at -1, -4. And so all the significant points for this particular curve were on our sketch. In fact, our sketch looks relatively decent up to knowing exactly how quickly it moves up and down on the ends. But those are a lot harder to actually do by hand. But the point here is that we got all the actually significant information about this curve in our sketch. Now, as you've already kind of seen from that last example, where there is a lot of stuff going on in these problems. They can take a lot of time just because we're going through every piece of information that we can. But we do want to go through a number of problems just to see what things can actually happen. So we're going to move on to problem 16. In this problem, we have a function y is equal to 2x over x squared minus 1. Now, the first thing we want from this is its domain. What is the domain of this function? Where can things actually go wrong? Well, it's going to go wrong if the denominator equals 0, and that's going to happen when x is either 1 or -1. So the domain is going to be everything else, wherever x is not -1 or 1. Also note that the numerator at 1 or -1 is not going to be 0. It's either 2 or -1. And so we will actually have vertical asymptotes at those y values. So we can already write down some information. We have y equals, not y. Vertical asymptotes are x equals values. We have two vertical asymptotes at x equals -1 and x equals 1. We can also talk about what horizontal asymptotes we have. We use the guidelines that we got from the last section. Remember, we compare the degree of the top and bottom. In this case, the degree of the top is 1, the degree of the bottom is 2. So the degree of the top is smaller than the degree of the bottom. And our guidelines say, that means our horizontal asymptote, there actually is one, and it's specifically y equals 0. Whenever the degree of the bottom is bigger, we get an asymptote specifically of y equals 0 on both sides when we're dealing with these rational functions. So we already have quite a bit of information about our curve without even actually having to do any sort of solving yet. Now the first thing we want to do, is see where is our function actually equal to 0. Compare this thing to 0. Get that number line for the first derivative. Not for the first derivative, for the original function. We're not to the derivative yet. Well, one thing about this is that a fraction equals 0 only when the numerator equals 0. So we don't have to worry about the denominator right this second. When is 2x equals 0? Well, that's going to happen when x equals 0. So we're going to have a number line for y. It's going to have 0 on it. But we also need to include any discontinuities. The fact that the function is not continuous at -1 or 1 means that I need to put those numbers on here as well. I actually have 4 different intervals to work with. I'm going to take test points for each of these intervals, from negative infinity to -1, from -1 to 0, from 0 to 1, and from 1 to infinity. I'm going to pick -2 and 2 for the bigger intervals. Fortunately, I'm going to have to pick a fraction for the intervals from -1 to 0 and from 0 to 1. So we just take these numbers, we plug them into the original function, this fraction right here. For -2, we end up with a -4/3. For -1/2, we end up with a +4/3. At 1/2, we end up with a -4/3. And at 2, we end up with a +4/3. So kind of interesting that we got only plus or minus at the same value here. But the important thing actually is what the sign is. We have a negative for that first interval, positive for the second one, then a negative and a positive. We're going to put those in here. Let's move on to the first derivative. Well, first of all, we need to differentiate it. What is the derivative of our function? What is the derivative of this fraction? Well, we're going to have to use the quotient rule. So we're going to take the derivative of the top times the bottom minus the top times the derivative of the bottom. The derivative of x squared minus 1 is 2x. All over the bottom squared. Now, if I want to set this equal to 0, I'm going to want to have a simpler version of this. Now, it would be possible to go ahead and set it equal to 0 right now, but it actually will help us even more when we talk about the second derivative, because we're going to have to differentiate this thing again. It's not as bad as it might seem, but it is going to take a little bit of work. But I'm going to go ahead and just simplify this numerator. Here we can distribute the 2. We have a 2x squared and a -2. Here we have a 2x times a 2x, which is a 4x squared. So we can combine the 2x squared with the -4x squared to get a -2x squared. But we also have that -2 that was there before. Now, okay, so this is what we have so far. We want to see where does this thing, well, first of all, what are the critical points? Where is this thing equal to 0? Where does this thing not exist? Well, if I'm setting this thing equal to 0, I'm really just setting the numerator equal to 0. We can divide this thing by -2. Or in other words, we have x squared is equal to -1. Well, we don't have any solutions here. Or at least no real solutions. And we only care about real numbers here. We're not trying to graph things in the complex plane. That's just not relevant here. So we're not going to have any new things from setting equal to 0. If we want to ask where does this not exist, well, the only place this fraction doesn't exist is when x equals plus or minus 1. Those are the only places that make the denominator equal to 0. But those were already discontinuities anyways. So we're going to have to continue to include those discontinuities of -1 and 1, but they're not going to be critical points. I do need to take test points, though. From -1 to 1, I can go ahead and put in -2. For 1 to infinity, I can go ahead and put 2. And finally, from -1 to 1, at least this time, unlike what we had before, we do actually have a number we can plug in. We can take y prime of 0. We get to plug those all into our fraction here. When we put in -2, the top actually becomes a -10, and on the bottom we get a 9. Specifically, this is a negative number. The bottom actually is going to be exactly the same thing. In fact, plus or minuses don't really matter here because we always square the x, so we get the same answer either way. When we plug in 0, on the other hand, we get a -2 on top. On the bottom, we have -1 squared, which is just going to be a positive 1. So we get a -2 here. Well, we actually got negative everywhere. So no matter what interval we're on, we're decreasing. The fact that we know where this thing is actually decreasing versus increasing will actually help a lot when we figure out how the function approaches its asymptotes. But we'll see that in a moment. We want to finish by looking at the second derivative. So, remind us what the first derivative was, because we're going to have to differentiate this thing again. Got to use that quotient rule again. So I'm going to take the derivative of the top. The derivative of -2x squared minus 2 is simply -4x. I'm going to take that times what's already on the bottom. We have x squared minus 1 squared. Then I subtract the top, but I also need to multiply by the derivative of the bottom. Now, the derivative of the bottom is going to be a little bit tricky just because we have a square of something that's not just x. So we're going to have to actually use the chain rule here, unless you want to actually go ahead and expand this thing out. And it turns out expanding it out is going to actually make it a little bit more complicated to simplify our result. So I'm going to use the chain rule here. So I have something squared. That means I'm going to take 2 times that something, but then I'm going to also need to multiply it by the derivative of the inside. Well, the something was x squared minus 1. The derivative of that x squared minus 1 is a 2x. And so that is our new numerator. Our denominator, we're going to take what we already had, this x squared minus 1 squared, and square it again. So a square of a square is a 4th power. And the reason why I wanted to use a chain rule here instead of expanding it out is because there is a cancellation that happens immediately because we did that. Specifically, both of our terms on top have an x squared minus 1 in them. This one has 1 copy of it. This one has 2 copies of it. The bottom has 4 copies of it. So I can basically take one of the copies from the bottom and divide each of our terms on top by that. Now remember, we do need to divide both terms. If we only divide one, that's a problem. For instance, we can't just take 2 of the copies from here and divide out this one without touching the x squared minus 1 over here. We specifically can do this because we end up having a term in both of these. So this one disappears, one of those disappears, so we're just left with one of them, and this decreases down to a 3. And that's going to save us a lot of work, believe me. Alright, but we still do want to simplify some things on the top. For instance, I'm going to take the -4x, I'm going to distribute it to both these two terms, because there is one of these still left. So -4x times x squared will be a -4x cubed. -4x times -1 will be a plus 4x. Here, well, for one thing, we can go ahead and use that negative that was there to actually make those both positives. That's actually really nice. And remember, we need to distribute to both the 2x squared and the 2, this 2 and the 2x. So 2x squared times 2 times 2x means that we're going to be adding in an 8x cubed. And then we have a 2 times 2 times 2x. We're going to be adding an 8x. Quite a bit of algebra going in here, but it is going to be worth it eventually. We can combine like terms. We have an 8x cubed and a minus 4x cubed. That's going to be simplified down to 4x cubed. Then we have a 4x plus an 8x. This time we add the numbers instead of subtracting them, and we get a 12x. And so this is our second derivative, which is not as bad as you might have thought it could have been. I mean, it was a lot of work to get there, but it is going to be useful. Now the question is, where is the second derivative equal to 0? Of course, it doesn't exist when x equals 1 or negative 1 because those make the denominator 0, but those are discontinuities of the original function. They're going to be on our number line, but we still want to find out places where the second derivative equals 0. Now, of course, that's only when the numerator equals 0. The numerator being 4x cubed plus 12x, we want to set that equal to 0. We can factor out a 4x from this. That leaves for here an x squared, and it leaves here a plus 3. X squared plus 3 is never 0 because it's always at least something that's 0 or higher plus a positive number. This thing here is never smaller than 3. That means the only possibility here is that x equals 0. That's the only time this expression can equal 0. So I'm going to have a number line for y double prime that's going to have 0 on it, but it's also going to have our discontinuities of negative 1 and 1. So actually, it's looking very similar to our number line for y already. We do want to take test points, though. I'm going to pick the same negative 2, negative 1/2, 1/2, and 2. But I need to plug those numbers now into our formula for y double prime. Now, we could use a calculator for this, or we could try to work it out by hand. We can also use the fact that we know the numerator actually factors. So we can essentially say for negative 2, we have 4 times 2, times negative 2, negative 2 in here, we have 4 plus 3 to give us a 7. And on the bottom, we have 4 minus 1, so a 3 cubed. Now, technically, we can't actually work this out. This is negative 56 over 27. But more specifically, if we don't want to have to try to work this out, we can note that there's only one factor in here that is a negative. The 4, the 7, and all the 3's on the bottom are not going to change the sign of this. It's the fact that we have a single negative 2 that makes this thing specifically a negative number. And that's all we really care about. We can do the same thing on each of these. So for negative 1/2, we have a 4. We have a negative 1/2. This thing, well, actually, we know this is a positive number. We don't even have to worry about it. We already said that this thing is always at least 3. And then on the bottom here, we have a negative 1/2, which turns into a 1/4, minus 1. Well, that's a negative 3/4, and that's cubed. So again, we can think about whether or not this is positive or negative without even having to work out the whole thing. We have a negative here. We have a negative here. This is cubed, but because it's cubed, we can think of it as 3 negatives. We have 1, 2, 3, 4. Total of 4 negatives. An even number of negatives means that we have a positive number here. We only need to know if it's positive or negative. Do the same thing for 1/2. We have 4, 1/2. We remember that's a positive number. Not even going to bother trying to work out what it is because it's not really too important. When we plug 1/2 into here, well, we get exactly the same thing as we got before. We got a negative 3/4. This time, we don't have the negative on the top. We only have a positive 1/2, and we still have those 3 negatives on the bottom. So overall, having 3 negatives, an odd number of negatives, we get a negative number. And then finally for 2, we do exactly the same thing as we did on this one. We still have the 4, we have the 2, and this turned into a 7 again. And then finally on the bottom, 2 squared minus 1 is a 3, and that's cubed. There's actually, there's no negatives in this at all. So this is a positive number. Alright, so we had negative here, negative here, and positive here. And so we have all this information about our particular function. Go ahead and make our axes. So first things first, we want to put in our asymptotes. And let's pick orange for that. We have an asymptote at negative 1. We have an asymptote of 1. And we also have another asymptote here of y equals 0. Our x-axis actually is an asymptote for this function. We want to identify any special points. Well, the only point that we got on our number lines that was not corresponding to a discontinuity was at 0. What happens at 0? Well, it's a place where the y equals 0. So that is not only the only x-intercept for our function, but it's also the only y-intercept. And because the concavity actually changes at 0, it's also the only inflection point. So that's a pretty significant point for this graph. But we know that our function has to be negative over here until we get to x equals negative 1. And it also has to be decreasing. And it has to approach 0. It has to approach this y equals 0 asymptote as we go off to negative infinity. And it has to be concave down. Well, concave down, might not even have to worry about that part. The only way that it could even satisfy these two pieces of information already is if we have something that looks like this. It starts coming from 0, just slowly coming from 0, and eventually decreasing down to negative infinity. Then after negative 1, well, now it has to be, well, it still has to be decreasing. Since it's decreasing, it has to be coming from positive infinity. It can't be coming from negative infinity, or it has to be increasing. That corresponds to the fact that we know our function is actually positive. So it definitely is positive over here. It's definitely decreasing. It has to be coming from this positive infinity. It also has to be concave up. So it's kind of part of a cup shape. But it's going to actually bottom out at 0. But it doesn't actually start increasing at any point. So let's... I want to come down here. Remember, it's part of a cup shape. It doesn't actually flatten out. It continues just decreasing the whole time. In fact, here at 0, it has a slope, I think, of negative 2, if I remember right. But at this point, it stops being more cup shape and being more cap shape. And it continues decreasing. As it goes negative, it's going to have to go to negative infinity as it approaches this particular asymptote. Finally, it continues decreasing, and it starts from being positive, and now it has to be concave up again, and it has to approach this asymptote at y equals 0. So we're going to get a shape like that. Sort of like that. Maybe I kind of didn't draw this middle part quite right. Maybe I should have emphasized the concavity a little bit more, but at least we got quite a bit of information about this particular curve. We got an idea of what this thing looks like. Of course, we can go ahead and compare with the actual graph of it. If we go ahead and use GeoGebra for this. Remember, our function is y equals 2x over x squared minus 1. Of course, we had our asymptotes of x equals 1 and x equals negative 1. We have our intercept, both x and y intercept, and our point of inflection at 0, 0. We definitely have this decreasing down to negative infinity on this side, coming from positive infinity with being a concave up, but swapping to concave down at A, at the origin, before going negative infinity and then coming back from positive infinity. So you probably noticed that in a lot of this, we actually didn't necessarily need all the piece information. In fact, we kind of got the idea of how to approach our asymptotes. We can get those basically from our y number line or from our y prime number line. Those pieces of information kind of just reinforce each other. So this is an example where we probably found a lot more information about our function than we actually needed to graph it. But that's not really the point here. The point here is just seeing how all this stuff actually works together. If we need all the information, well, maybe that's why we found it all. If we didn't need it all to get the graph, well, in practice, we can go ahead and just look at the parts that we think we need. But sometimes it can be hard to tell whether or not we do need more information or not. Because, for instance, if it's positive from -1 to 0, maybe it were to come down, maybe it's coming from that positive infinity, but it can then kind of just does something like that. Maybe we can't tell it doesn't do something like that until we take a look at the first derivative. So, you can't always tell exactly what's going on until you have all these pieces of information. Now, this video has gone on quite a long time, and we've only gone through 2 examples. I do want to go through some more examples, but I don't want to just shove it all into one video. So I'm going to look at a couple more examples, but I'm going to do that in a separate video. So I'll see you there for some further examples.